Lesson 33, the photoelectric effect, is a big lesson. We'll do this lesson in two parts. And before we do that, let's quickly review what we learned yesterday. The big concept we learned yesterday was that light comes in little packages or little pieces called quanta or photons. And just to review that concept using the example I did yesterday, if you're a little person and you're going to someday grow into a big person, there are an infinite amount of heights that you will reach in between being this height and this height, right? You don't go from being 112 centimeters to 113 centimeters instantaneously. You have to go to 112.5 and 112.468 and 112.4689210.5, blah blah blah. You get the point. So that's continuous. But light is not continuous. It comes in little packages, and we call this quantization, which means you can exist at this level or you can exist at this level, but you can't exist at an intermediate level, somewhere in between those. All right, so you can be a 2 or you can be a 4, but you can't be a 3 in light. And as I said, that will become increasingly important as we go through this unit. So now let's go on to the photoelectric effect, and we'll start with a little PhET demonstration. Where is it? Here it is. All right, what do we have here? What do we have here? We have a light source, and we have a piece of metal, and in this case you can see the piece of metal is sodium. So this little gray strip here, that's a piece of sodium. And then we have an electric circuit set up here. We won't worry about that until the second part of the unit. But what we're going to do is we're going to shine some light on this metal. So here we go. The intensity is 0. Let's increase the intensity to 100%. So we're shining, looks like kind of pinkish light right now on this metal. And what's happening? Absolutely nothing. That is so unimpressive and disappointing. However, why don't we change the color of that light? Let's make it more red. If we make it more red, we're increasing the wavelength, and therefore we're decreasing the frequency. Nothing happened. Nothing happened. What if we go all the way to infrared? Nothing's happened. Let's try the other way. Let's move it to yellow. Nope. No. Oh, something happened right there. As soon as we moved it from yellow to green approximately, what's happening here? What are these little things? Oh, that happened and then it didn't happen. There we go. So we're in the green, we're shining green light on sodium metal, and these are electrons. These are electrons that have been ejected from the surface of the sodium metal. All right, and you can see that they're going in. Let's increase this a little bit. Let's, as I increase the frequency, in other words, I'm decreasing the wavelength, so I'm going closer to UV, to invisible light here, you can see that the electrons, some of the electrons are getting faster. Let's really ramp it up there. Ooh, and now some of these electrons are going really fast, and some of these electrons are going slow, but you can see that they're all going kind of one or the other speed. And if I increase it to really high on the UV scale, they're zipping along quite a phenomenal speed. So let's go back to here. So there we go. So we've got some electrons going fast, some electrons going slow. And why? Because we're just shining light, something with no mass on this metal, and all of a sudden these electrons, which have mass, are being ejected from the surface. This is the photoelectric effect. And then you can mess around with this and you can change it to zinc. If I go zinc, oh, that doesn't work for zinc. What should I do for zinc? Well, I'm obviously gonna have to increase the frequency, and all of a sudden, so I need a higher frequency of light to shine on zinc to get the electrons to be ejected from the surface. Now, why are some of them going fast and some of them going slow? Well, the ones that are going fast are the ones that are right on the surface of the metal. And the ones that are going slower are kind of deep in the surface. So what happens is this light, which has energy, the energy of the light is transferred to the metal, to the electrons in the metal, and it gives them energy. It gives them kinetic energy, and they're ejected from the, if there's enough energy from this light source, it gives the electrons enough energy to be liberated from the sodium, and they will be ejected into free space. So that's and as I said, the reason some of them are going slower is because some of them are deeper in the surface, and so they need more energy. They need some energy to get them to the surface, and then what's remaining will give them kinetic energy. That's why if we slow it down a little, you'll see some going slow and some going fast. All right, so that's the photoelectric effect, and really what the photoelectric effect is, it's conservation of energy, which we will get to. All right, we'll stop that for now. We'll come back to that for the second part. And on to our lesson. And here we go, the photoelectric effect. So I just kind of explained all this, so I don't need to really go through that. So Einstein's explanation of the photoelectric effect. There are some things we need to know mathematically. The first is, as you can see when we do in the PhET demonstration, when we increase the frequency, the electrons were ejected at faster speeds. So this is what we call the threshold frequency. And again, I'm just going to backtrack a little to the previous lesson. In the previous lesson, we learned this formula here, E equals HF. E equals HF is the energy of one photon. What we're going to do now is take this formula and we're going to put a little naught there, and that little naught means the threshold frequency. In other words, that's the lowest frequency that will liberate electrons from the surface of the metal. If the frequency is any lower than that, then the electrons don't have enough energy to get off the metal. If the frequency is higher than that, then they will be ejected then they'll have more energy. So that's the threshold frequency. It's the lowest frequency for any given metal that will not allow electrons to leave the surface. The work function is basically this formula right here. It's this value here. We're just going to change it to this. The work function is the amount of energy. So if F naught is the threshold frequency, you multiply it by H and you get the work function. And the work function is the amount of energy that you need to knock electrons off the surface. And as it says in your notes, every metal has its own work function, since different metals hold on to their electrons with different strengths. And we demonstrated that with two different metals on the PhET demonstration. Okay, so here we go. We've got a new formula right here. The work function equals HF naught. And we can do a couple of problems related to that. Example number 1 is pretty straightforward. Determine the threshold frequency of a metal with a work function of 10 EV, 10 electron volts. So it's given to you in electron volts. So therefore, we're going to use the 4.14 times 10 to the negative 15 electron volts seconds. For Planck's constant. Determine the threshold frequency, that's what we want to find. And we're given the work function, 10 eV. And for Planck's constant, we're going to use the 4.14 times 10 to the negative 15 electron volt seconds. Rearrange your formula, plug in the numbers. I don't think we need to go through that. It's just 10 divided by 4.14 times 10 to the negative 15 electron volt seconds, and you end up with an answer of 2.4 times 10 to the 15 hertz. So that is the minimum frequency that will knock electrons off this given material. Example number 2 says determine the work function of a metal in joules. In joules, this time we're trying to find W, and we're finding it in joules, so we're going to use the 6.63 times 10 to the negative 34 joule seconds for Planck's constant. If the maximum threshold wavelength, so this time they don't give you the frequency, they give you wavelength. And you can do that in 2 steps, or you can do that in 1 step. So let's just let's do it in, well, we're going to do it in 2 steps, but 1 step really, but it's going to be 2 steps. Confused? I am. We know this formula. We know this formula. We can combine those to make 1 formula. We're going to call it the threshold wavelength. That's why I'm just going to put the naught there. So we can manipulate the formula, or we can combine those formulas and derive this new formula and plug in the numbers. Or you can just do this one first, and then, this one first, and then this one here, and get your answer that way. So that's a 2-step. This is the 1 step, but really it's 2 steps anyway. And that will yield an answer of 1.18 times 10 to the negative 18 joules. Okay, so that's the first part of this lesson, just the basics of the photoelectric effect, shining a light, EMR, on a metal. If the frequency is high enough, in other words, if the energy is high enough, then some of the electrons are liberated from the surface. The higher the frequency, the faster, the more energy those electrons have, and therefore, we're talking about kinetic energy here. So soak that in, enjoy it, and we'll continue with part 2.